joining us from different time zones. On behalf of Institute for Integrated Hydro Environment Research, I am pleased to welcome you to today's webinar on advances in flow measurement techniques. So this is a kind of unique global collaboration between Europe, Nepal, China, India, as well as America. So this webinar brings together researchers, professionals, and students who share a common interest in cutting-edge hydraulic instrumentation technology and its role in solving complex water-related challenges. Our focus today is in one of the evolving technologies such as particle image velocimetry and particle tracking velocimetry (PTV), which are revolutionizing the way we analyze the fluid motion and understand the sediment and flow behavior in both laboratory as well as field setting. We are honored to host two distinguished speakers, Dr. Subhajit Kadia from Technical University of Munich, Germany, and Dr. Liu Chieseng from Hefei University of Technology, China. Both have conducted pioneering research using high-resolution flow measurement techniques and will be sharing their insights on experimental design, data interpretation, and the broader impact of advanced instrumentation in hydraulics. Following the presentation, we'll have an open discussion session where you are encouraged to ask questions or share your reflection. You can also post your question in the chat, and the presenter will try to answer all of your questions. Toward the end, we'll also hear brief closing remarks from invited observers. We'll offer additional perspective on the topic and the session overall. So before we begin the technical session, let me take a moment to introduce the organizing institution, the Institute for Integrated Hydro Environment Research, IIHR. So IIHR is an independent non-profit research institute based in Nepal, dedicated to advancing scientific knowledge and innovation in the field of water, environmental, and sustainable development. IIHR brings together the researchers, practitioners, and policymakers to address complex hydro-environmental challenges through interdisciplinary approaches. Its work spans across hydrology, hydraulics, sediment transport, environmental flow assessment, and climate change adaptation, with strong emphasis on field-based research, capacity building, and regional as well as international collaboration. Today's webinar reflects IHR's ongoing commitment to fostering knowledge exchange among different parts of the world and among academia, industry, and promoting the advancement in experimental and applied water sciences. To know more about us or to contact for the collaborative venture, visit us at iihr.org.np. So without further delay, let us begin with the first presentation. It is my pleasure to introduce our first speaker, Dr. Subhajit Kadia, who is currently serving as a postdoctoral researcher in Chair of Hydraulic Engineering at Technical University of Munich, Germany, and soon joining as an academic faculty at IIT. Dr. Kadia has completed his PhD in engineering from Norwegian University of Science and Technology, NTNU, where he focused on experimental and computational approaches in hydraulic engineering. His research explored a wide range of advanced topics, including supercritical flow in curved and straight channel, sediment bypass system, nonlinear weights, and turbulence modeling using CFD. Prior to his academic career, he also spent more than 4 years in Indian hydropower sector, gaining on hands-on experience with hydraulic structure during his tenure at WBSEDCL, one of the power department in West Bengal. Today, he will share with one of his research focusing on the investigation of sediment bypass tunnel in lab using PTV and video footage. He will also highlight the importance of this novel approaches not only to the research in lab, but wider application to investigate critical problem in hydraulics. The floor is yours, Dr. Kadia. You can share your presentation now, and I'll ask audience to listen him to here. Thank you.
Thank you, Kamal. Just a second. Do you see the presentation?
Yes, I can see and hear you. So if anyone has question during the presentation, they can just write on chat and then I'll take them later.
Yeah, good afternoon from Europe and morning and evening in other parts of the world. And thank you, Kamal and other members of IHR for initiating this webinar on advances in fluid measurement techniques. I will particularly focus on sediment bypass tunnel, critical challenges with sediment bypass tunnel, and the experimental work that I performed using volumetric particle tracking velocimetry and high-speed camera. First, I will cover background of sediment bypass tunnel, particularly supercritical narrow channel flow. And this work was done as part of my PhD. I would say the last part of my PhD in Sweden. As you can see on the right-hand side on photograph of the experimental setup. And this work has been published in Advances in Water Resources at the end of last year. So let's start with supercritical narrow channel flow. So we know supercritical flow, that is inertia, and the ratio of inertia and gravity is more than one. So if we consider a very simple cross section, a rectangular cross section, then V by root over GH is more than one, that is supercritical flow. So this supercritical flow is observed in natural stream as well as in different hydraulic structure. For example, let's just steep rivers and also hydraulic structure, let's say spillways and weirs and barrages and also dam outlet structures.
Excuse me, Kadia sir.
Sorry.
So I cannot see your presentation moving. Maybe you need to share the whole screen instead of sharing just presentation.
Okay, sorry. Okay, just a second. Give me, sorry. Sorry.
Yeah, you can share the whole screen and then just start the presentation. I think it will work. Yeah. And so still I can only see your.
What you can see now. Can you see the, I think this should work now.
No, not yet. So
It's
No,
showing
you
sharing
should
the screen.
select the entire screen. I think you are selecting a window. During the share setting, if you do entire screen,
here
you can move
share the
between.
entire screen of the computer itself. So it should work fine if you share the whole screen of the computer.
If I share the PowerPoint, what is happening?
If you only share the PowerPoint, we do not see your PowerPoint moving. So instead of that,
Just
in the
a second.
in the share.
Sorry, I'm more used to Microsoft Teams, so.
So in the share, you can share the entire screen, which should be on the top screens.
Yeah, just a second. Sorry
Okay.
again.
The share on the green button.
It should work. This screen 3. Why is it not working?
If you have multiple screens, so then it may switch. So I think you need to plug off the multiple screen also.
What about now?
So we are still seeing just the presentation, the
Now?
first page only.
I think now it should work. Please try the presentation
Just
mode.
A second. Yeah. Sure. Okay, then select. Yeah, I think now it should work. What you can see now?
Still the same. Okay. Still the same, yeah. Yeah, you can also like click one
now?
slide. Oh yeah,
I think
now it's fine.
working.
Good.
Yeah.
Just a second.
Thanks a lot.
Oh, sorry for this interruption. Okay, so I'll start with the slide. I hope supercritical flow you already understood. So this kind of flow situation is available, and we observe it in hydraulic structure. Also, we encounter in natural stream, like in high, let's say, mountainous streams. We observe supercritical flows. And what is narrow channel flow? Is this the channel width B divided by flow depth V by H is less than or equal to 5? That is called narrow channel flow. And throughout my whole presentation, these terms will be repeated so many times: supercritical flow and narrow channel flow. So just be aware of that. And my research was mainly focused on this hydraulic structure sediment bypass tunnels. Why sediment bypass tunnel? We know the reservoir sedimentation issue. So every year, around 1% of reservoir capacity is lost due to reservoir sedimentation. If we break into different countries, as we can see the severe situation in, let's say, countries like China, Tanzania, And also, but in Nepal and India, still I would say it's not as severe as compared to those countries, but in on average, still it is quite challenging for the upcoming generation, I would say, for the sustainability of the reservoir capacity. Here also we can see after 1980s or 2000, not many new dams were built, and nowadays if we compare all the dams, most of the dams are quite old and they are approaching towards their design life. One of the main reason is the reservoir capacity lost due to the reservoir sedimentation. Also, because of the population growth, the per capita water availability is decreasing even more steeply as compared to the net water availability. Also, a reason is lack of sustainable management because most of previous designs are just designed based on the lifespan of reservoir rather than designing for a sustainable way so that it can last for a longer time, and also designs for not tackling the issue of reservoir sedimentation, which is basically being noticed in the last couple of decades. And what are these sediment management strategies? Broadly, these can be divided into four categories. One is sediment yield reduction. At catchment level, we basically take measures so that the incoming sediment to the reservoir is less. Then sediment routing, we can basically route the sediment around the reservoir or through the reservoir. And sediment bypass tunnel belongs to this second category. Also, third category is removal of already deposited sediment from the reservoirs. Let's say hydraulic dredging or mechanical dredging and this kind of approaches. And adaptive strategies are like say design measures. For example, let's say we rise the dam height, then obviously we have more storage. So these kind of example are adaptive strategies. This is a general plan and longitudinal view of a sediment bypass tunnel where you can see. Just a second. Yeah, here you can see in the upstream part of the reservoir, we have the intake structure and the guiding structure to divert the flow. And then the water, sediment-laden water is driven to the intake structure, and then the water, sediment-laden water return back to the river in the downstream site. And also, if I have observed that the number of application of sediment bypass tunnel had increased in the last 1 decade, as you can see on the right-hand side. This is a longitudinal view of sediment bypass tunnels. So after the intake, generally we have a steep accelerating section so that no sediment is deposited in the intake part. After that, we have decelerating flow region, followed by that supercritical uniform flow condition. That is the longest part of sediment bypass tunnel, and then we return the sediment-laden water in the outlet. What are the main advantages? That it is an active sediment management strategy. So we are basically diverting the sediment while it is incoming to the reservoir rather than already deposited sediments. By routing the sediments, we are basically reducing the amount of sediment incoming to the reservoir. As a result of that, remaining life of the reservoir will be increased. And also it helps to maintain the river sediment continuity in the river, also improve the morphological and ecological aspect of the surrounding areas. And my research mainly focused on this long part of sediment bypass tunnel, that is supercritical uniform flow condition. While inspecting the existing sediment bypass tunnels, I found that most of the sediment bypass tunnels are designed for flow number between 1.4 to 3, that is supercritical flow, aspect ratio between 1.1 to 2.3, that is less than 5, that means narrow channel, and tunnel filling ratio between 50 to 80%, that is mostly open channel flow condition. However, there are some example of pipe flow conditions also. This is it should work. Video is not working. Just a second. Unfortunately, the video is not working somehow. Okay, we move forward. So what are the critical challenges with this bypass tunnel design? So as I said, narrow channel flow, and what is basically the importance of narrow channel flow? So because of narrow channel flow, generally the flow condition is 3D due to the effect of the boundaries. And we observe the secondary currents of type 2, as you can see in these photos. It shows a comparison between open channel flow, that is the plot A and C, and the pipe flow, that is plot B. So here we can see, due to the difference in effect of the free surface and the midway depth of duct flow, we have different types of secondary currents of type 2. However, the bottom corner contains both the solid wall. So there are some comparison result observed for open channel between open channel flow and duct flow, particularly for very, very narrow channels. And why these secondary currents are formed? Due to the difference between the lateral and vertical turbulence and anisotropy, or it is also known as Reynolds stress anisotropy. So due to this Reynolds stress anisotropy, these secondary currents of type 2 are driven, and they can redistribute the flow properties across the channel and can affect the flow parameters. For example, the 2D flow velocity, which is basically converts to 3D velocity profile. So we observe that the maximum velocity is not observed at the free surface, but at some distance below the free surface. And this phenomena is called the velocity dip, as we can also see here, the velocity dip. Also, the bed shear stress undulates due to the bottom vortex, this bottom vortex toward the bed. So as a result of the secondary current, the flow properties can change significantly, that can affect the sediment transport and erosion or abrasion in case of sediment bypass tunnel. However, very limited studies are done for supercritical flow due to the limitation of both experimental and numerical approaches. The second issue is the hydroabrasion. So after very severe, let's say, flood event, we can observe that abrasion up to even meters of depth. This is one example of sediment bypass tunnel in Switzerland. So what is basically hydroabrasion? Is basically removal, or you can say removal of the invert or bed of sediment bypass tunnel due to the mechanical action of the particles, particularly in saltation. So when the particles are basically taking small jumps, they're hitting the invert of the bypass tunnel. As a result of this erosion is taking place. However, we have to be very careful that the saltation and its effect, that is the abrasion, is not exactly same like in scour, that what we observed in rivers. And I will discuss more about this difference in the future in the next slides. What is the governing factor is the particle size is very important. So it's not always that the largest particle that will create aberration, because the largest particle might be in rolling motion and the smallest particle might be in suspension motion. So it is the intermediate particle size that is very important for this particular effect. However, in case of bend, this aberration pattern takes a twist, I would say, as you can see here in this figure, one example from Japanese sediment bypass tunnel, where we observe deeper aberration toward the inner wall of sediment bypass tunnel as compared to the outer wall. There was some hypothesis, yes, probably the secondary currents of type 1 due to the curvature is affecting the flow properties and bed shear stress and sediment transport, that is leading to invertebration. However, no detailed investigation was done, only some field studies are available. And now let's compare the scouring in curved channel as compared to the abrasion. So basically, due to this main core-region vortex and increase in the bed shear stress toward the outer wall, we have deeper scouring toward the outer wall in case of movable bed or in reverse. However, in case of sediment bypass tunnel, it is actually different. We have a fixed bed, let's say concrete bed. The bed shear stress was not studied previously, and it was anticipated that the bed shear stress is higher toward the inner wall, and as a reason of that, the abrasion is taking place more towards the inner wall. However, that is not correct, and that is the major finding of the study. So the lack of knowledge, previous studies, they anticipated that the sediments are pushed, sediments are concentrating toward the inner wall, and the base shear stress is higher toward the inner wall. As a result of that, the abrasion is deeper toward the inner wall. However, that was questionable, and that no 3D experimental data were available, only 1D experiment were performed for supercritical flows. So I took this opportunity and conducted experimental work with 3D particle tracking velocity. So what were the major research questions is how the channel curvature affects the flow properties, bed shear stress, and sediment movements in supercritical flows, and how these parameters are interrelated to each other and leading to this kind of non-uniform invert abrasion for sediment bypass tunnel. That will be very useful for designing this kind of sediment bypass tunnels or similar structures. So specific objectives were to experimentally investigate these parameters in a scaled down sediment bypass tunnel model, and then to inspect how these properties are interrelated and how they are inducing this non-uniform invert abrasion, and also how the sediment transport patterns are redistributed across the channel. This was also already published, like I said. In addition to that, also supercritical flow in veins causes surface waves, cross waves. As a result of that, the free surface is also quite complicated. That's also I investigated using experiment and CFT modeling that was published in a separate paper. So this is the example case study I took, solid sediment bypass tunnel. I scaled down the solid sediment bypass tunnel with the scale factor of 1:2, and flow similitude was performed. So on the right-hand side, you see the parameters of the scaled model. This is the plan view of the experimental setup. So this channel, you can see this is the curved channel. So I did the PTB measurement at 6 volumes, volume A to volume V along the channel, and the recording of the sediment movements were performed at 3 locations. That is at the entrance of the bend, at the midway of the bend, and in the downstream of the bend. 3 different supercritical narrow channel flow conditions were tested as shown in the table, and the spherical sediments were from 4 to 12 millimeter were injected at 4 meter upstream of the bend, and then the lateral movement of these particles were inspected using a high-speed camera. So this is the downstream view of the PTB setup. As we can see here, if we closely look into the setup, so we have this camera assembly that contains 4 camera to basically get the 3D view of the particles. And it contains an LED and not laser. And the LED was placed below the channel. So this whole setup was made, this curved channel was made of plexiglass. That was very difficult to construct. Why plexiglass? Because of the requirement of this visual accessibility to the bottom as well as to the side, because of we can't do anything from the surface because of the free surface complexity. And this setup was Lavish on mini-seeker arrow. And some more details about the setup. And the most important part is the PTB tracking or particle tracking method that is called check the box method. It is quite novel approach. And for each and every experiment, I took 10,000 images at a frequency of 800, that is 12.5 seconds. And the CDL particles were 60 micron polyamide particles. And now let's go inside to the tracking approach. So this particle tracking velocimetry called check the box. It starts with the conventional tracking method, that is the triangulation method. So we have images from cameras from different angles. So then we use the triangulation method to basically track the particles in a 3-dimensional space. And from 5th time steps onwards, we try to project the particles. So up to 4th time step, we have the particle locations, we know the path. So then we try to project the particle path in the 5th time steps and onwards. So when we have an estimated particle location, then we basically check the particle position in a 3-dimensional field with a resolution of 0.1 pixel to match with the intensity of the images. So by doing that, we try to reconstruct the particle, and eventually we try to track the particles in a Lagrangian field. Like on the right-hand side, you see the raw image. After temporal and spatial filtering, we have the images on the right-hand side. And after this check the box method particle tracking, we get the particle motion. And then we basically convert it into a regular grid to get the flow properties like you can see on the right-hand side. And the second part was capturing the particle motion, like the sediment motions, as you can see. So basically the bottom camera placed below the channel, it was used to record the particle motions, particles between 4 millimeter and 12 millimeters. And then basically we observed how the particles are moving across the channel and how it is actually related to, whether it is related to bed shear stress and how it is related to the abrasion patterns. This is video. It's a very interesting video. I really wanted to show it. I hope it works at least. Oh no. Sorry, this is also not
You
working.
can play from outside.
Yeah, I will play it later once it is done. Okay, that's not an issue. Because it is in this folder, so it should work automatically. I don't know why is it not working. Okay, so this video I will show about the experimental setup, and basically we took a drone video, and that's a very interesting video I will show. So some in results. So here you can see the longitudinal velocity distribution across the channel at 6 sections, so section A to section F, and these sections are at the midway of the volumes of measurement, that is volume A to volume F. So we had 6 volumetric measurement, and these sections are basically the center of those volumes, representing the cross-sectional distribution of the flow. For 3 discharges, 45, 70, and 95 liter per second. So in section A is placed upstream of the bend. So this is placed in the straight channel part. So if we see, if we closely look into the results in section D, that is the halfway or midway of the bend, and for the downstream, we see the secondary currents of type 1 or the curvature-induced secondary currents are observed, like outer wall vortex and mean co-region vortex. However, and the straight upstream part, we didn't observe the secondary currents of type 2 that I showed in the first challenge. And that I did numerically, but in this experimental, we could not still observe the secondary currents of type 2. However, I did some comparison with previous result at the straight section, at the midway of the section, that is y by I00. As we can see, it basically follows the modified log-Weck law. So we can and also the longitudinal turbulence intensity, vertical turbulence intensity, and the shear stress distribution are comparable with previous studies. However, the lateral turbulent intensity VRMS could not be compared to the previous studies, and that is because of the limitation of the setup, because it could not recognize or could not accurately measure the velocity fluctuation in the lateral direction due to the limitation of the experiment with small stereo angle. And also, we could not measure the secondary currents of type 2 accurately in the upstream part. Like here, what we observe, what we expect. So if we closely look into the results, this diagonal component of the secondary current basically pushing the high momentum fluids toward the outer wall and outer wall bottom corner. And then we have this downflow that is increasing the near bed velocity gradient and increasing the bed shear stress. However, this horizontal component, this is very important. This one is pushing the high momentum fluids toward the inner wall, and this is responsible for sediment transport toward the inner wall. Although this vertical component toward the outer wall is increasing the bed shear stress, this horizontal component, near bed horizontal component, is pushing particles toward the inner wall, and that is inducing the deeper abrasion toward the inner wall. Although the bed shear stress is higher toward the outer wall. So briefly, this secondary currents, mainly the diagonal flow, is distributing the flow properties. So we see the higher bed shear stress toward the outer wall, and this near bed horizontal component is pushing the particles toward the inner wall. So although the bed shear stress is higher toward the outer wall, the sediment is concentrated or pushed toward the inner wall. And as a result of that, we see deeper abrasion toward the inner wall. So this abrasion pattern is not directly related to the bed shear stress magnitude. And this bed shear stress distribution is comparable with previous subcritical flow simulation using LES. However, it contradicts with previous anticipation that they anticipated that the bed shear stress is higher toward the inner wall. Some more result about the turbulent intensity, longitudinal turbulent intensity. Now, if we can recall the secondary currents and the component from the previous slide, we can see the turbulent intensity is changing due to the secondary currents of type 1. In the high momentum fluid, we can see lower longitudinal turbulent intensity, and due to this horizontal component, again, the turbulent intensity is changing. Similarly, for vertical turbulence intensity also, these are related or closely, basically, interrelated to the secondary currents. And now comparison of the sediment transport, you can see in the upstream part of the bed or in the straight part, the sediments are basically spread across the whole channel. However, as the secondary currents of type 1 develop in the curved channel, in further downstream, we see the sediments are pushed toward the inner wall. Although we have to remember the bed CST is higher toward the outer wall, and that was a very interesting phenomena that was observed. And yeah, finally we have the reason why we have deeper ablation toward the inner wall. Another video, unfortunately, did not work. So let's come to the major conclusion. So as we observe that toward up to the quarter of the bend, that is section D, the secondary currents of type 1 didn't have much influence on the flow distribution and also sediment, but up or beyond the half of beyond the midway of the bend, we see due to the development of the secondary currents, the flow property is modified across the channel. The high momentum fluids are pushed towards the outer wall. The bed shear stress is increasing towards the outer wall. However, the near bed horizontal components toward the inner wall is pushing the particles toward the inner wall, and the particles, once they are pushed toward the inner wall, they remain attached to the inner wall, although the bed shear stress is low toward the inner wall. So now the general conclusion is that yes, although the bed shear stress is higher toward the outer wall, it is the secondary current that is the main governing force behind the concentration of the particles towards the inner wall. And as we see that the particles are concentrating toward the inner wall, this can induce this deeper abrasion towards the inner wall as compared to the outer wall, what is observed in actual sediment bypass tunnels. So we might need to consider a conservative design toward the inner wall of sediment bypass tunnel as compared to the outer wall. And also we have to be careful with differentiating scour and abrasion. We observe that in more movable bed on river, we have deeper scouring toward the outer wall due to the secondary currents and bed shear stress. However, due to the secondary currents and near bed horizontal component, the sediments are pushed toward the inner wall, and the abrasion pattern is that the deeper abrasion is observed toward the inner wall. So it might look an opposite phenomena. However, if we closely monitor the actual reason, then those two phenomena can be differentiated clearly. However, some limitations of the study, the secondary currents could not be measured, or secondary currents of type 2 could not be measured at section A, and also the outer wall vortex could not be measured accurately for all the section. And what is the main reason is the small stereo angle between the cameras. If we observe the camera assembly, all those cameras were basically connected in one assembly with very small stereo angle between 3.6 and 4.2 degrees. So that's a lesson we learned. And then currently also I'm focusing on alias simulation for supercritical flows and also Lagrangian particle modeling, like to basically reflect my experimental finding using using DEM, discrete element modeling, and also trying to do further particle motion analysis from my videos, so that we can basically rethink about the existing saltation ablation model and whether we can improve the existing knowledge and the models. As I said, the free surface wave and the cross waves also form in supercritical flow. This is just a glimpse of that results, how the free surface undulates and whether we can simulate or we can reflect using CFD modeling in open form. So that I managed to do it. And as you can see, the error in the flow depth, the location of the wave maxima, and also the horizontal location of the wave maxima are quite reasonable from simulation as compared to the experimental work. Yeah, I'd like to thank my supervisor and collaborators who helped in this whole work. These are references, and yeah, thank you so much for your patience.
Thanks a lot, Subhajit. I think you can show the video now.
Yeah, that's what I was thinking. If I get time, I can show that. Yeah. Just a second. Yeah, that was a bit surprising. It should work because I tried it before and it worked. Okay, so I will show the model video. Okay, I just need to check. Okay. Yeah, can you see the video?
Yeah, now we can see the video. Yeah.
Yeah, so yeah, again, thanks to Par for making this wonderful video using drones. So we are moving from upstream of the channel We have the PTB setup here, and then we can see the curved lexical section of the bypass tunnel. And then again, we have state section in the downstream. And then we have energy distribution structure, or basically, then it is going to the underground reservoir, and then we are recirculating the water. And one more video, I will just show very quickly the recording of the particles. Maybe I took more time than I was assigned. Sorry for that. Yeah, can you see this one?
Yeah, I can see.
Yeah, so this is I can see that the particles are pushed toward the inner wall and then they remain attached toward the inner wall. This was recorded for 70 liter per second and at the center of the paint. Yeah, thank you so much.
Okay, thanks a lot, Dr. Subhajit Khadia. That was an interesting presentation on the use of PTV method to for the physical modeling of sediment bypass tunnel. It was quite interesting, and then we'll get back to you for further questions later. Then, for now, we have our speaker number 2, Dr. Liu Chiecheng. So our second speaker, Dr. Liu Chiecheng, is a lecturer at Hefei University of Technology in China. Dr. Chiecheng earned his PhD from Ohio University and he spent a year as a visiting academic at University of Cambridge in UK. His research centers on river dynamics, fluid mechanics, and sediment transport, with a particular emphasis on settling behavior and interaction of particles in flowing water. Dr. Chiecheng has made a significant contribution to the field with 14 published research papers as well as 13 authorized patents and 1 monograph. He has also led and contributed to numerous national research projects funded by National Natural Science Foundation of China. In this webinar, he will present his insight on high precision flow measurement tools, PIV and PTV, highlighting their application in understanding sediment motion and improving hydraulic research methodology, and as well as possibility of field application. The floor is yours, Dr. Liu. Thank you.
Okay, I will share my screen. Can you see my screen?
Yeah, we can see your screen. Can you go into the presenter mode?
Yes.
Yeah, that's good.
Yeah. Hello everyone. I'm Jiaqing Liu, a lecturer at Hefei University of Technology. The title of my presentation is Settling characteristic and interparticle interactions of sediments with different surface morphologies. First of all, I will introduce some methods for measuring flow velocity in experiments. Flow velocity is one of the main characteristic parameters for determining fluid motion. It is not only the starting point for theoretical analysis, but also the standard for verifying theories and provides a reliable basis for engineering. At present, the flow velocity measurement instrument and method include pitot tube, tidal flow velocity meter, ultrasonic testing technology, particle imaging velocity measurement technology, and so on. We can see the picture. Yeah. The pitot tube measurement principle is simple to operate, which is the most widely used and longest standing flow velocity measurement instrument. However, only one dimension measurement can be carried out, resulting in relative large measurement errors. Moreover, the inlet of the pitot tube must each reach deeply into the measurement point in the fluid, which interferes with the flow state and is not suitable for the measurement of turbulence and boundary layers. The basic principle of pedal flow velocity meter is to place the pedal fixed on the sensor bracket at the measurement point in the fluid, with the pedal facing the directions of the flow. Due to the action of dynamic water pressure, it rotates. The greater the flow velocity and the faster the rotation. The pedal flow velocity meter can only perform one-dimension contact measurement, which interferes with the flow state and is not suitable for measurement of turbulence and boundary layers. When the flow velocity is large, the measurement accuracy is high. However, when the fluid velocity is small, the measurement error is large. Second is ADV. ADV utilizes the Doppler effect for three-dimensional velocity measurement, featuring high temporary and spatial revolutions. During measurement, there is no need for calibration, and flow velocity data can be directly obtained. For ADV, since the propagation speed of sound wave in air and liquid is different. When measuring the fluids, the transmitting and the receiving probe need to be placed in the fluid. Although there is a certain distance between the measurement point and the transmitting and receiving device, it will still interfere with the flow state. Then I will introduce the PIV. PIV is a modern flow measurement technology that uses image precision technology to measure the instantaneous velocity field in fluid in a full-field, non-contact, and undisturbed manner. It breaks through the fact that the traditional single-point measurement instruments cannot measure the transition flow field of the whole of the entire flow field. PIV can simultaneously measure the two-dimensional or three-dimensional velocity vectors or multiple measurement points in two-dimension slides or three-dimension space, and can accurately capture instantaneous vertices. It is an effective technique for studying turbulence. Then I will introduce some of the research during my doctoral studies. The part one is research background and research content. In hydraulic engineering, nature river and lakes, particle cycling is one of the basic hydraulic properties of sediment. The cycling velocity and the influence of the surrounding fluid and the interaction between particles during its cycling not only determine the state of sediment transport, but also serve as the basis for understanding sediment environment effect. Natural sediment particles have complex morphology features. We can see the picture below. According to the different morphology characteristics, sediment can be divided into spherical particles with high roundness, angular particle with shape and edge, and porous particle with pore structure. In our study, sediment particles are generalized into spherical, cubic, and porous spherical particles. We can see the picture. Our research content is first, particle settlement rule, flow characteristics, and interaction between particles. We take spherical particle as an example. The effect of initial spacing, Reynolds numbers, and particle number on settling progress of two or multiple particles released side by side was studied. The differences and similarities between it and the single particle cycling were compared and analyzed. Second is influence of angular characteristics on particle settlement and interaction. We take cubic particle as an example. Starting from the single particle, the influence of the position of the edges and the Reynolds numbers on settlement was studied. Then the influence of the angular characteristics on interaction between two and multiple particles is explored. It is compared and analyzed with the settling rule of spherical particles, and the similarity and difference between them are sorted. Third is influence of Bohr characteristics on particle settlement and interaction. We take porous spherical particles as an example. The effect of porosity, pore structure, and Reynolds numbers on the settling of porous single particles are studied. Based on this, the effect of porosity and the initial spacing on the interaction between porous doped particles were investigated. The difference and similarity between particle settling and that of solid sphere are compared. The part 2 is experimental method and setup. In our experiment, the settling tank, we can see the figure in the left. The settling tank is transparent, plexi content, and the length, width and height is 40 and 80 cm. With the selected experimental liquid, the settling velocity of particles in all cases can be ensured to be stable. In our experiment, the liquid is glycerin and water mixture of different concentrations. It is used to change the viscosity of liquid and thus adjust the Reynolds numbers. Yeah, this picture is our particles in the experiment. We can see the particle motions were captured by PTV. We can know the particle motion, and the flow fields were captured by PIV. Now I will introduce the PIV in our experiment. PIV is a measurement technique that allows for capturing velocity fields in fractions of a second. Its development started in the 1980s of the last century based on early work on the field of laser spectral photography. The advantage of PIV over competing techniques as the laser Doppler velocimeter is the simultaneous measurement of complete velocity fields that enable studies of complex flow, including vertical structures, flow separation, turbulence characters. Powerful experimental methods like PIV represent tools for advancement and observative computations used for validation of math model or as guidance in developing new theories where existing models either have shortcoming or do not exist. PIV is a non-intrusive optical technique used to measure instantaneous velocity fields in fluid. The core principles are summarized as flow. First is tracer particle seeding. Small tracer particles are dispersed in the fluid. This particle must fully follow the flow to ensure accurately illumination and imaging the content. And the third is imaging interrogation. And the fourth is velocity field reconstruction. Yeah, we can see the picture. This is precision area. This is important for the PIV. Then the declared PIV principle can be referred to in the following books. Yeah. The PIV system adopted in our experiment mainly include a camera, a continuous laser, and a controller. Whole glasses bear tracer particles, and an imaging question card, a high-performance computer, and PIV imaging processing software. And the parameter of our PIV system in this list. Yeah. Then I will show some video in our in my another experiment. It is a confluence flow. Yeah, we can see the flow field by captured by the PIV. Then it's the part 3. Part 3 is cycling rule and the interaction of spherical particles. The cycling characteristics of single spherical particles in static fluid have been basically clarified, where the cycling characteristics of group particles are quite complex and are not well understood. In particular, the interaction between two particles are not yet clarified. So we studied the dual particle cycling first. The interaction between two spherical particles released side by side is repulsion, and the cycling progress can be divided into 3 stages: the stage of constant particle spacing, and the stage of rapid repulsion, and the stage of stable repulsion. Then the repulsion is mainly affected by initial spacing and Reynolds numbers. And when initial spacing larger than 5 particle size, the repulsion can be ignored. This is the flow field around the dual particles. And then we extend our research to more particles. We can see this is 3 particles and this is 4 particles, and we also got the flow field around the particles. Okay. Then part 4 is settling rule and the interaction of cubic particles. Different from spherical particle, the settling of cubic particles is not a straight line, and it's a S-shaped curve or spiral curve. We can see the video. Yeah. Then we find 2 modes, and at the surface mode, a pair of stable vertices are formed in the rear, and the trailing vertices are the same side. A particle can remain stable during cycling. We can see the figure in the left. Then it's the model. Then it's the edge mode. We can see the figure in the right. It is difficult to form stable vertices pairs in the rear, and the particle tend to rotate during cycling. And this is the flow field. Then we also studied the dual cubic particle cycling. During cycling, the 2 particles repel each other and are accompanied by particle rotation. And the 2 particles always rotate inward. Yeah, we can see the video. Similar to spheres, the cycling process of the dual cubic particle is divided into 3 stages based on repulsion. And in stage 3, there is a significant difference between cubic and spherical particles. Then is part 5. Part 5 is settling rule and interaction of porous particles. The settling trajectory of porous spherical particles is similar to that of solid spherical particles. The settling trajectories are straight line in vertical directions. Yeah, we can see the video and the picture. And this is the flow field around the porous particle. In the left is large porosities, and in the right is small porosities. And when porosity is small, it is more like solid particle. Then, when the porosity is relatively small, the particle permeability is small, and the fluid is difficult to enter the weak zone through the pores. But from both sides of the particles to the weak zone, forming a pair of obviously stable and symmetry vertices between the particles. We can see the figure at left. Then, when porosity is larger, the particle permeability is large, and the fluid can enter the weak zone through the pore. Therefore, stable vertices cannot be formed behind the particles, and the instead of the weak makes the particle settling in a slightly curved spiral path. Yeah, we also studied the porous particle settling. Yeah, we can see the video. The settling of the settling trajectory of porous particles is similar to that of solid spherical particles. The interaction is also repulsion, and it also can be divided into 3 stages. Yeah, this is the flow field around the porous particles. Then then is the conclusion. Yeah, you can just see it. Okay, thank you. This is all my presentation.
Kamal, you're muted.
Thanks a lot, Kim. Thanks a lot, Dr. Liu. So it was a wonderful presentation on PIB and PTB methods to analyze the settling properties of different kind of the particle and different morphology of the particles. So yeah, it was a wonderful presentation from both of the speakers. They highlighted the uses of the different PIB and PTB technology in the respective field. And now we can take on questions. So if anyone from the audience have the question, they can raise their hand or unmute themselves and ask to speaker directly, or they can write in the chat. Else I will start asking some questions myself. So anyone there?
Yeah, I have like one question for each of the speakers. So like first to Subhajit, like you told that your experiment can be used to like validate numerical models. Can you like elaborate on that? So how the existing models are working in the high fruit number conditions, and then how your experiment can help to validate or advance the numerical models?
Yeah,
And
thank you.
yeah.
Sorry. Yeah, please go ahead.
Yeah, I like next question to another speaker. So yeah, this
Okay,
question
then
for you.
maybe
Yeah.
I could take a this one. Okay, yeah, thank you for highlighting a very important point. Like at the end, as an outlook, I suggested about the CFD modeling. So yes, initially I had a master student who was working. So we started with runs modeling, very simple one, and just to see how far the runs can do because the natural turbulence and anisotropy is there due to the curvature. So in the curved model, yeah, to some extent runs can simulate the flow properties, and the student has observed that it can also simulate the particles. However, we know the limitation of the lens, and so in the future we want to extend to LES. However, for LES we will require supercomputer and maybe billions of cells, not even million. So because of the high velocity and to still keep the Y plus or Z plus less than 5 to resolve the viscous sublayer, we would require very, very high computational power. So yeah, we started with runs and hopefully in the future we will go ahead with LES so that some of the limitation of the experimental finding that could not capture the secondary currents of type 2 that can also be done in LES. But that will take time. I could see in 5 to 10 years time that would be possible, but not in near 1 or 2 years, let's say.
Yeah, thank you, Subrit. And I have another question for Liu. So, Liu, thank you very much. So, your like works like seems very advanced. So, uh, I mean, like how your work can be used in applicative field like in settling basins in hydropower sector. So you have settling particles and the efficiency of that settling particles in the settling basin governs a lot of things regarding efficiency of settling basin and also hydro the turbine abrasion later. So how your work can improve the efficiency of like settling basins in hydropower sector.
Yeah, thank you. Uh, because the settling velocity is very important for the hydraulic engineering and for natural rivers. So in my research, the aim is to is 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 to give a new formula to predict the settling velocity of different particle of different of different sediment. So we want to improve the settling velocity prediction. Yeah, it's
Oh, okay.
my aim.
So like, will this formula like right now we use kind of like empirical formula, for example, like Vetter's equations or something like that. So will that formula be available because this is really very important in like South Asian context where we have really big challenges with that. So will that formula be available very soon or is in the stage of development?
Yes, we just development the formula the formula to predict more more accurate accurately. Yeah.
Oh, okay. Yeah, it's really a good context for like Nepal Hydropower Association. Yeah. Thank you. Thank you for being a speaker. Yeah. Yeah.
Thank you.
Yeah.
Okay, I don't see any questions from the audience. Then I would like to ask question to Shubhojit myself once. I saw that you used a LED setup for the PTB, and I didn't quite get it. What kind of shading material did you use in the setup?
Yeah, thank you for the nice question. Yes, the setup contains LED, so it's the whole setup is it contains 72 I think high intensity LEDs, and the seeding particles were it's 60 micron with a density of 1.03 gram per cc. It was polyarmide. It was from Lavision only. They had the seeding particles, and the density is very close to water, 1.03, and it was 60 micron. So that's yeah.
So do you think that I think this LED is more safer than laser techniques that we use? So do you think that this can be commercially available and that can be used in open channel flow or the top of the sediment bypass tunnel to characterize the 2D flow properties in real engineering practice?
Yes, 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 it will be possible, but the optical access will always be the challenging part. Whether
Yeah.
you are doing PIV or PTV like this volumetric setup, I think that is the more challenge. If we have some optical, let's say windows available in tunnels or something, then obviously we can also do full field measurement. But yes, one of the most important part of this whole setup was the LED because that's very I think with laser it's always challenging with a lot of let's say precaution and also the safety hazards, but the LED is very convenient, I would say, and it's also for volumetric field it worked quite well. Yeah.
Thank you. And we have one question from the audience, Mr. Thaneshwar Khatri. So, to both of you speakers, what are the latest technique to measure flow velocity in big rivers during the flooding situation? So, in the flooding situation, we have this highly turbid flow. So, can't use any intrusive device like we can still use, but it's always a risk to use those devices. And what are the non-intrusive techniques that can be used to measure in flow in big rivers during flooding situation?
Yeah,
Subhojit, I think you can. Yeah.
yeah, that's always the challenging question that we want to avoid, I would say, as a laboratory like experienced person, because we know these things are what we are doing. It's very difficult to represent exactly on the field. So we have to go to some of the conventional techniques, I would say, for actual field, some intrusive measurement, yes, just to get some, let's say, some data or some result. And then if you want to do further research, then obviously you have to go back to academic part, do some experimental part or do some simulation part. But at the field, I would say ADCP kind of instrument is used for bed load transport or also conventional method. Uh, but large scale, yeah, it's still difficult with this kind of advanced technology, I would say. It's very difficult to use this, let's say, PIB or PTB setup in case of actual river situation. So we have to go back to conventional methods, unfortunately.
Uh, Chiachang, do you have any idea on like what are the latest available methodologies? Maybe that they are developing it in China in big rivers like Yellow and Yangtze, what they do during the big flooding situation? Do they use the conventional method or they still use the hydrological station and rating curves?
Yeah. Well, we use the ADCP when in the river. When it during a flood, we just used remote sensing and and unmanned aerial vehicles. Yeah, you know.
Okay.
Maybe you can
Yeah.
write in chat also, Li Jiuqing is also okay for that. Yeah.
Yeah. And
Yeah.
also like I would like to say that there are like certain large scale particle velocimetry which can be used, which does not exactly give you the depth, but also it can give you the 2D flow field. Like you can place a camera on top of the bridge or somewhere in a stable place, and you can continuously take the picture, and then you can generate the velocity vector on the top, and then assume that you have a certain kind of known geometry below by which you can extrapolate the velocity field on the cross section, and then you can estimate the flood. But it's still under development, and it is prone to a lot of error. So that has been in practice for a couple of years with the advancement of AI and other camera system. So that is also one of the technologies currently used to measure this high flood level. But for the accurate flood discharge, you still have to go with the traditional method. And ADCP can be a good choice given that you have very stable system which can still float on the water.
Kamalji, I have one question to Dr. Kadia. Can I put my question?
Yeah. Go on.
He has said that at generally we know that at outer bands shear stress is higher compared to the inner bands. However, in this case, which Dr. Kadia did, most of the erosion are taking place at the inner bands. So I think it is due to the abrasion caused by the movement of particles at the inner bands. Is it?
Yes, yes, absolutely right. So, and this is opposite of the phenomena we observed in case of scouring in river bends. That is mainly due to the base shear stress magnitude and the downward component of the secondary current. And this horizontal component is pushing the particles towards the inner wall. And once particles are concentrating toward the inner wall, it is causing more abrasion toward the inner wall as compared to the outer wall. Yeah, you are absolutely right.
Thank you.
And one general question for Shubhajit, maybe you already told that in case of Nepal and India, the sediment can be a huge issue, but with the situation of Nepal, we do not yet have like big reservoirs in operation, and we are planning to build a lot of hydropower, which will have a complete seasonal reservoir or at least intermediate reservoir, which we would in theory have the sediment bypass tunnel.
Mhm.
And due to like complicated geography, of course the sediment bypass tunnel would not be very straight, or they have to have certain bend. And
Yeah.
in such cases, like what would be your suggestion to like how to properly design a
Yeah.
sediment bypass tunnel? And do you think that the laboratory investigation is a must, and after building the sediment bypass tunnel, real prototype investigation is also a must?
Yeah, yeah, very, very important point. Like, yeah, the results or the data I showed is from 2009. So, but now I would say in last couple of years, people are also planning and designing sediment bypass tunnel for Nepal. Even in India, the condition is quite severe as compared to the plot that I showed. It was 15, 16 years back. Also in India, we have now Dam Safety Act. So reservoir sedimentation is a very like very, very important point nowadays in planning and designing. And then, sorry, the second part was the design. Yeah, yeah, yeah.
Yeah.
So yeah, with the curvature, the first and foremost important point is to avoid the curvature as far as possible. But we know from design and also depending on the condition of the rock, we have to go for the curvature. Then this kind of like fundamental study and also the field observation that was done in Switzerland and also in USA and also Japan, they suggest some let's say some discrete patch where we can observe deeper abrasion. So the best suggestion would be to design to go for a conservative design toward the inner wall, or let's say in the bend part further up a bit upstream and downstream of the bend we can have a higher strength concrete as compared to other part of the bypass tunnel. Or we can go for metal also for this very localized part of sediment bypass tunnel. Because if you want to do, let's say, metal lining throughout the whole tunnel, then the cost will go very, very high. So maybe this short part of the bend and further downstream, hopefully in the future we can do more simulation. So we can run simulation and then get the sediment concentration in the tunnel and then basically have a conservative design in that part of the tunnel, and the remaining part of the tunnel still could be having a more economical design, say.
Thanks a lot, Subhajit, for answering. And do we have any more questions from the audience you would like to ask to our speakers? Also, you can contact them later if you have any
Yeah, yeah.
question related to the research field and the application.
So
So we
I have
have
like
one.
one
Yeah.
question to Dr. Kadia. So, can you give? It's very kind of very coarse. Can you give like, for example, if you have 1 kilometers of SPT,
Mhm.
so with your research work, so in terms of cost, so how much that will reduce your research? Like only just lining that curve section, so how much cost it will reduce by lining whole of the SPT and lining only your section, and that is curve part.
That's a
Just a
very
tentative
interesting
guess.
question.
Yeah.
I must say I don't have any value in my mind because it will
Maybe.
depend on the size, like the cross section and the diameter of the tunnel also.
Uh,
Maybe I have to go back to very like some literatures where they have the data from actual bypass tunnel, but unfortunately I don't have it in my mind now. I'm so
Okay.
sorry
Yeah,
for that.
please. Thank you.
Yeah.
Yeah.
But it can
So,
still be quite like if you don't apply the same material throughout the tunnel, then as compared to only considering at some part with very high strength concrete or let's say steel lining, then obviously it will save a considerable amount of money because whatever you do with bypass tunnel, still the abrasion will happen. It is happening with most of the bypass tunnel in Switzerland, in Japan, and Taiwan, and also USA. Whatever you do, still it will happen. It's very tricky because some material is working by some bypass tunnel, but the same material is not working in other bypass tunnel. So it's a bit of trial and error, but now people have experience, so those experience and those literatures are helping for let's say latest design. So it's bit case to case basis, but yeah, obviously there are design measures that we should follow.
okay,
Thank
more
you.
questions from the audience, like in industries like oil, gas, or wastewater management, how do the new flow measurement techniques handle hydration of the fluids itself? So do you have any like instrumentation methodology that can handle high viscous flow or the contaminated or like highly turbid nature of the flow?
Yeah, maybe I just quickly can comment like this. I'm not so sure about the hibiscus, but at least the contaminated fluid I can see. Let's say they can be treated as the particles. So let's say if you have a PTB kind of setup, still you can basically measure those movements of this contaminated particle. So that is possible because this PTB can also be upgraded to a system where you can track both the flow and the particle, like the not the seeding particle, but other particle, let's say sediment or contaminated particle simultaneously. So this system is quite advanced and you can have more upgraded version, obviously more costly, but that can be used for contaminated particles. Yeah.
Next question from Gopal Singh Bhandari, sir. So can we relate the narrow channel results with broad channel characteristics?
Not really.
Yeah.
Yes, because the narrow channel is very, I would say, very complicated as compared to as compared to wide rivers, because then we have two-dimensional flow, and they basically the design is much more simple as compared to narrow channel. And let's say this whole research mainly focused on this kind of hydraulic structure, bypass tunnel and narrow channel. So yeah, but the flow and the sediment pattern is much more complicated in case of narrow channel as compared to a wider river or wider channel.
And okay, what are the spatial and temporal filtering used in PTB measurements?
Yes, there are different techniques, and right now I would say I don't remember actual technique, but maybe Diksha, maybe could you please write an email? Then I can share it with you. I think that would be better. I don't remember the exact filtering that I use right now. Yeah.
Okay, I think we also have Mr. Anup Khanal, so he's involved in a lot of instrumentation in field of hydrology and hydraulics in Nepal. So earlier question we had like how can we measure the large discharge in the river during the flooding condition? So I think he is quite well experienced in the field. I think if he can share his ideas on how we are doing such laborious tasks in Nepal, then all the general audience that they can have the idea. So Anup sir, can you elaborate on this issue?
Thank you. Very nice to see the in-depth PTV and PIB. So it's in terms of the research, and I think we have to work a lot to make it the application use. So currently, for the sediment measurement, we are using which is
Fortunately, we can't hear
more
you
developed.
properly.
Anup
Yeah,
sir, we
sorry.
have a disturb in our line, so can you please repeat what you said
Okay,
earlier?
so Am I audible?
Yeah, you are audible, but we have some broken issue, so you can also type if you like.
Just let me. I will. I'll change my Wi-Fi. Okay. Hello. Is it better
Yes.
now?
Yeah, we can hear you properly.
I just switched my Wi-Fi to the better one. So, well, yeah, we have of challenges, and normally iPods uh, are the parameters we need to measure for the flooding conditions to rescue the people and for the early warning system. So, discussed earlier, the intrusive method is not much applicable monitoring, and we have to go for the some kind of non-contact measurement. So for that, um, can be mounted over the water surface. So for example, in the bridge, so, two, three sensors. This sensor is that it can measure only the surface mass.
Okay.
To get the velocity profile from the numerical modeling, just use the empirical relationship like 80% or 90% would be the mean velocity of the and for the low flow and the medium useful in energy measure opposites, and we use like current meters. So slide that the velocity profile is totally different. So what we assume is the ideal section, never ideal section in reality. So the track the velocity profile along the depth. So that would be a better idea to use for the low and the medium, but they are applicable for the high plot conditions. So uh, yeah, it's rough, but we don't have any other alternatives because we even can't drive ADCP across the river in the flood situation because the safety matters also. So yeah, we can have some good estimate with and somehow okay for and regarding the sediment good that PIB and PTB is a source and maybe it takes some applicable formula. But currently we are using the we are using the acoustic back scattering system. Yes. It transmits different frequency of the sound, and then it will examine the reflection. So by evaluating the cloud density, measure how much sediment concentration is there in the water. Able to produce a good, accurate results in every context. So we have already implemented 2-3 hydropower projects with ABS. So we can accuracy up to 10%, or for example, error of the 10%, but that is very optimistic in terms of sediment measurements because sediment dynamics we know that. So even you take the measurement in the same time, 10%. So from the sensor, if we target to achieve 10%, only the 10% use. We hope TB methods will also give more ideas to develop formula in the sediment settling. So maybe in future we are hopeful that this research will contribute for the sediment measurement. Yeah. That's
Yeah, thanks a lot, Anup sir, for your insight into the use of different kind of methodology or the combination of the methodology during the low flow, middle flow, and the high flow situation, as well explained on the use of acoustic pressure scatter technology to measure the uh, sediment concentration, which is especially applicable in case of hydropower operation. So the hydropower operator, they need to know how to schedule the turbine operation and save the turbine from a lot of abrasion and mechanical wear and tear. So that was a quite a good explanation on the real world implication of this kind of technology. And from the talk from the speaker on particle tracking velocimetry and particle image velocimetry, there are some advancement in the field regarding the field application of PIB as well as the PTB. So in case of the PIB, it is actually like we have seen some of the research where they have produced PIB techniques that can be used in the field that are especially used to monitor the ecohydraulics in the field. That means to monitor how the living organism dynamics are played in the aquatic habitat. So there are some PIB setup that use the mild type of laser that can mostly characterize the flow field in like 3D flow field inside the real field in the river as well as. And the as for the PTB, it is also used in the field to get the 2D flow vectors. So there have been some progress in the field, and in near future, I think we can have a viable solution which can use the both technique to get more detailed uh, flow field as well as the particle characteristics, because these are really like sophisticated methodology that are used in the laboratory scale. So we need to adapt this to the real prototype scale also, so that we can formulate a good question as well as good physical understanding of the processes that happens in the river system as well as in different kind of water resources project. So these are like quite interesting era to live and see the gradual development of this technology. So I think we are done with our question answer session. So I would like to ask Mr. Rakesh Kumar Chaudhary, CEO of IIHR, to give some remarks regarding uh, our webinar. And after that, I'll also ask observer to stay so that I can have feedback and their closing remarks on the whole webinar session. The floor is yours, Mr. Rakesh, sir.
Thank you. Thank you, Kamal sir. Good morning, good evening, everyone. I am truly honored to have the opportunity to propose the vote of thanks as well as the closing remarks for today's webinar. Thank you all for being here. First and foremost, I would like to extend my profound gratitude to eminent speakers, Dr. Subhajit Kadia and Dr. Liu Chiosang, for their immensely insightful talk on advances in flow measurement techniques using advanced instruments such as the PIB and PTB for flow analysis, and especially for the analysis of flow, and which is very much efficient in the fluid dynamics study. And similarly, it is also useful in the study of sediment transport. I hope the discussion has been very much effective for both researchers and practitioners. Similarly, I would like to extend my sincere thanks to all the observers, especially Dr. I think he's not available here, Dr. Salish Chitrikar, Nirmal Lama, Gopal Singh Bandai, and Engineer Anup Khanal for their insightful opinion on today's topics and their application in industry. How this instrumentation can be applied in the flow measurement in the real fields like as the rivers and canals, these things. Now I would like to thanks to all the participants for their active involvement and all collaborating organizations. Last but not least, I would like to express my sincere thanks to all organizing committee members for their dedicated efforts behind the scenes. Now I would not like to extend my talks too much. With these two words, I would like to conclude my words here. Thank you all. Have a good day.
Okay, thanks a lot, Mr. Rakesh. So now it's time for the overall insight from the webinar through the lens of our observers. So Dr. Sailesh Chitrakar, if you are here, so please, we can have your kind words on
Yeah.
what you think about this webinar. Thank you.
Yeah, can you hear me?
Yeah, you're audible.
Hello, can you hear me?
Yes, we hear you well.
Okay. Thank you very much, all the organizers and um, yeah, IIHR for organizing this great webinar. I personally enjoyed a lot, and it was very fruitful, especially also because I am not from civil engineering background. I am from mechanical engineering background, and I happened to do my PhD also in the field of PIB, but it was PIV in the hydropower turbines. So I was in Trondheim also in NTNU back in 2015 when I was using these PIV instruments to capture the full flow field around the guide vanes of Francis turbines to see the secondary flow inside the turbines. And it was really good to see that the field of or the application of PIV and PTV is also very prominent in the bypass tunnels and also in the settling basins. And although I'm not very familiar with all the civil engineering stuffs, but I was also part of Hydrosen project, and now we are also part of Renew Hydro project, where we are collaborating with Elena Pumar and her team. I think Subhajit also knows about this project. So that's basically about interdisciplinary research between civil engineering and mechanical engineering from the perspective of excessive sedimentation in the hydropower plants. And I think these kind of the interdisciplinary research would help to have the holistic approach of on the solution of the problems. And I really look forward to more collaborations in this sector of mitigating the problems of sedimentation and also sediment erosion in the turbines. So with that, I really would like to thank once again all the organizers for inviting me and making a whole new perspective, and also making me realize a lot of other things that I already knew about PIV measurements. So thank you very much.
Thanks a lot, Dr. Sailesh Chitrakar. Now we have Engineer Gopal S. Pandari from IOE. He's also one of the observers in our webinar, so we had kind support from him. So I would like to hear some words from him about the webinar. Thank you.
Okay, thank you, Kamal Pandey sir, and IHR for invitation as a participant and observer for this webinar and representing IOE. And it was very great to know about in-depth research about the PIV and PTV techniques for flow measurement and settlement of characteristics of the sediment. And I would like to thank Dr. Subhajit Kadia for its insightful research on PTV techniques for measuring the scoring or abrasion of the bypass tunnels. I think it's very useful in Nepal in future because we have to build storage type hydropower dams. And due to the topography of Nepal, I think it will not be possible to have straight channels at every possible scenarios. So this research will be very uh, useful for designing those types of bypass tunnels and uh, other for this PIV techniques. I think it will be very useful in designing settling basins in hydropower projects and water supply projects and sanitary projects like settling basins or sedimentation tanks. Although I am not background from this water resource engineering, but it was always great to know advances in civil engineering sectors. And I would also like to thank Mr. and Dr. Liu Zhaiqing for his insightful research on PIB techniques for particle velocity measurement. And also like to thank IIHR for continuous uh, research programs or like this webinar or this group discussions like in resource works or in water resource. And it will be our pleasure if we can involve some of our students from IOE for those who are interested in water resource sectors. If we need some kind of some students or master students or PhD student, we can allocate some student with good students who are interested in those kinds of projects. And at last, thank you, IHR, for considering IOE as an observer. And Kamal sir, over to you.
Thanks a lot. That was very insightful opinion from Mr. Vandari about the academia and collaboration. And I would like to invite Mr. Anup Khanal again to share on his view about the webinar as an observer from IES. Over to you, Mr. Anup Khanal, sir.
Thank you also for choosing me as an observer. And I would like to the presenter, both presenter, Dr. Subhajit Gadia and Dr. Liu, for their insightful presentation. And yeah, this has brought some discussion. Sorry, is there any side noise coming? Or?
I think now it's good.
I would like to bring this talk in a, when we sit for the design of the settling basin, we that is 1940s. So it's to overcome this on PTB and PIB. That it's a good start, and we hope we will get a good solution. Settling so that we can optimize our structures and other hydraulic basins projects. So ultimate goal should be to contribute to the real world problem solving scenario. So this theory gaining from this research would definitely practical world. I hope so, and it should be all of our aim that after our research, such output should be applicable to the real world, so that we will be a good contributor to the industry. So yeah, it was a very good webinar, and we wish I to continue such in innovative webinars. So yeah, thank you, and it's a very good program from our eyes. Yeah, thanks.
Okay, thanks a lot, Anup sir. So that was really kind of you, such kind word. And I think we will continue with the collaboration in future with you to advance the hydraulic measurement technique and uses in the field, applying from theory to the practical. And we also have our next observer, Engineer Nimral Lama from Nepal Hydropower Association. Unfortunately, she already left because of some errands, and we'd like to extend thanks to NHF for being an observer in our webinar. And special thanks to our organizing committee, Mr. Ishwar, Khem, Naresh, Ravi, Pratyush, all of the guys from the IHR. They have did a fantastic job in organizing such a webinar and putting together the group of experts in the field. I would like to thank on behalf of the Institute. And also thanks to all of our participants who joined across different institutions and countries. Your questions and engagement helped make this meaningful knowledge sharing experience. We are really happy to have that. We encourage you to stay connected with IIHR through our website and upcoming events as we continue promoting scientific collaboration and capacity building in water and environmental sector. The recording of today's session along with presentation material will be shared in our group website. So you can reach to our group website as well as we can follow in our LinkedIn page. With that, I would like to officially conclude today's session. Thank you once again, and we look forward to seeing you at future IHR events. Stay tuned in our LinkedIn webpage to know about upcoming future plans. Thank you all. Thanks a lot, and thank you again for wonderful speakers we had at our today webinar. Okay, have a good day, good evening, and good night to different part of the world. Thank you.